This lesson is on heat transfer. In other words, how does thermal energy move? How does it transfer from one thing to another? So the first thing we've got to do is we've got to understand what the word heat means as opposed to the word temperature. We tend to think of them interchangeably, but heat isn't the same thing as temperature. Two objects can have can hold the same amount of heat while being different in temperature, because some objects are easier to make their temperature heat up than others. And heat's measured in joules, obviously, and temperature is measured in Kelvin or in degrees Celsius, but not in degrees Kelvin. So let's try to tease this out, figure out what we mean by them being different. So imagine a very hot day. Imagine it's July, it's 104 degrees Fahrenheit, and it's 3 p.m. The sun's been out baking your front yard all day long. So you have a concrete sidewalk, a metal tray, or a kiddie pool, all of which have been laying out in your yard. We all have metal trays laying out in your yard, I assume. I'm not the only one. And we're going to ask ourselves, okay, if you had to go stand in or on one of those things barefoot, the concrete sidewalk would be pretty uncomfortable. I don't think we would want to do that. The metal tray would actually probably hurt, and the kiddie pool, while not ideal, it would be okay. I mean, you would step in there and it would be warm water. It's not like you would prefer to swim in something that a kiddie pool with a small amount of water that's been out in the sun all day is going to get warm, but it's not going to hurt. In fact, if you stood on the metal tray, you might then want to jump into the kiddie pool to kind of cool off and heal your burns. So what is it that's different? Why do these things, which all are being exposed to the same heat source, the sun, why do they get to different temperatures? If we actually were to take thermometers and measure the temperature of these things, they would actually be different. This would probably have the lowest temperature, and this would be the highest, and the concrete sidewalk would be somewhere in between. So that is because of this thing called specific heat. Specific heat is a measure of the energy needed to raise the temperature. So I can put the same amount of heat into two different things, and if one has a high specific heat, then that means it takes a lot of energy to increase the temperature. If something has a low specific heat, it's not going to take as much energy to increase the temperature. And so we can kind of reason from this that the specific heat of water is high and the specific heat of some kinds of metal, steel, is low, meaning it doesn't take a lot of heat to raise the temperature. Here it does take a lot of heat to raise the temperature, and this would be in between again. So can we validate that claim? In the textbook that I use, page 279 has a list of specific heats, and I don't know if you can see them on the video or not, but if we look at these, it doesn't have a concrete, I don't think. But if we look at generally, maybe just compare the metals to the water. The metals, aluminum's 900, brass is 376. But if we compare those to water down there in the bottom right is 4,180. It's like, 40 to 50 to, it's many times higher than, oops, I didn't have it all in there, did I? Than the metals. And so, yeah, so it actually kind of all fits together with the data. So how do these go together? Well, we have a formula that we're going to use for these problems that goes Q equals mc delta T. And Q would be the thermal energy measured in joules. So that would be your heat source with the sun or stove or flame of some sort. M, as always, stands for mass in kilograms. And C, that is our specific heat term. That's what we just got done talking about. Each element, each different substance is going to have its own specific heat. And this is either going to be given in the problem, or it's the thing you're going to be trying to solve for in the problem, or you will get it off of that chart. Like I said, for if you happen to be in my class, the book we're currently using, that can be found on page 279. If you have any physics class, you will be able to just go look in the back at the appendix and find a specific heat, and see what page that those tables are going to be on. Finally, the last part of this formula is delta T. Now, delta means difference, it means change, and so just like always, that's going to be the final temperature minus the beginning or initial temperature. You might see this written as F minus TF minus TI. You might see it as T2 minus T1, but the idea is the same. It's the end minus the beginning. So, what kinds of problems can we work with this? So let's say that we had to calculate the amount of heat needed to raise a 5.8 kilogram block of lead from 22 degrees Celsius to 87 degrees Celsius. I guess I didn't talk about, I need to go back a second. I need to talk about a couple of things. You know what? I am not good at this. So C, I didn't talk about its unit. So if you look at it, we need to have a unit that when we multiply it by kilograms and by degrees Celsius or Kelvin, that we spit out joules. So that would work out to be, so we got kilograms times, let's just use Kelvin, times something has to spit out joules. Well, the thing that has to be in that parentheses, this unit for specific heat, has to be joules per kilogram Kelvin, or joules per kilogram degrees Celsius. So why am I just going back either or? Normally we have to be very, very clear on which temperature unit we use, because it makes a big difference. Like in the ideal gas law or any gas law in chemistry, we know that we have to use Celsius or Kelvin, not Celsius. So why can we do whichever for these problems? Well, here's why. It has to do with this change term. The change in a temperature in degrees Celsius and the change in the temperature in Kelvin happens to be the same. I'll give you an example. Let's think about the change to go from the melting point of water to the boiling point of water. And let's work this out two ways. Let's do it in Celsius. The melting point of water in degrees Celsius is 0 degrees Celsius, and the boiling point of water is 100 degrees Celsius. So if we do the final minus the initial, 100 minus 0, we get 100 degrees Celsius. 100 minus 0 is 100. Now let's work out the same problem for Kelvin. What's the melting point of water in Kelvin? Well, it's 273. And the boiling point? Well, it's 373. And so 373 minus 273 is, once again, it's 100. So the change in Kelvin to Celsius is the same. And since this formula only uses changes, then we really can use either one as long as we're being consistent, because we're just going to subtract them, and the differences in Celsius and the differences in Kelvin will be the same number. Now we're ready for this problem. So let's calculate the heat needed to raise a 5.0 kilogram block of lead from 22 degrees to 87 degrees Celsius. So it's looking for the heat, so we are looking for Q, that's the heat, And so our formula for that is MC delta T. And that's going to be, the mass is 5.0. So it's going to be in kilograms always for physics. And C, remember that number depends on what you have. This is lead. So we're going to look on our table. I believe we saw it a little bit ago. Lead has a C value of 130, a specific heat of 130. And I should probably not be lazy on my units. So kilograms goes with the 5. And then we're going to have the C value, the specific heat is 130. What would we say? Joules per kilogram Kelvin. And then we're going to do delta T. Delta T is the change, the final temperature minus the beginning temperature. So this is the final here. This is the beginning. So remember, when the temperature goes up, then the final minus the beginning will be a positive number. And when it's going down, then the final minus the beginning will be a negative number. And that tells you whether heat is going into or out of the system. So a positive Q, positive heat, would indicate that energy is going into the system, and a negative one would tell you that thermal energy is coming out. In any case, the final minus the initial 87 minus 22 is 65. And again, I could use Kelvin or Celsius. In either case, it would be 65. Please do not, what you don't want to do is take a change in temperature and then add 273 to it. That's never going to work. You can't add 273 to the change. You can add 273 to this and 273 to this, and then subtract them, but you would still get 65. So whether I'm working this in Celsius or in Kelvin, I'm going to get 65 either way. So now we can see that kilograms cancels, kelvins cancels, and the only unit left is joules. So we can get out our favorite calculator now and type all this in. We got 5 times 130 times 65, and that's 42,250 joules, or 42.25 kilojoules would also be another way to put that. How many liters of liquid water can be brought to its normal boiling point from 25 degrees Celsius by 2.5 megajoules? That's a big M. It looks a little bit like a little m. Megajoules of heat. So the formula we're working with is MC delta T. So let's see what we can plug in. We have the heat, it's 2.5 megajoules. You can't use megajoules unless you change your C term unit, because the C term is going to be in joules. So you got to convert that 2.5 megajoules into joules. We won't go through how to do that. Equals the mass. Now, it's not given us the mass, so we're going to leave that term alone. C is, this time we're dealing with liquid water. Quick note here, water has different specific heats based on its different states. In liquid state, it has a different specific heat than it does in solid or as the steam. So ice, steam, and liquid water all have different C specific heats. If we look up this one on the table, it's 4180 joules per kilogram Kelvin. And the change in temperature is we're going to its normal boiling point. That would be its boiling point at standard pressure, which for water is 100 degrees Celsius. So our final temperature is 100 degrees Celsius, and our initial is 25 degrees Celsius, which gives you 75 degrees Celsius. I'm actually going to write my term as 75 this time, in Celsius this time, just to show you that it doesn't make any difference. I just change, this can be C or K, this can be C or K. So if you look now, we can see that Celsius cancels out, joules is on each side of the equation, so it's going to cancel out. And so I can get a mass term in kilograms if I divide this out. So I'm going to divide the 4180, divide the 75, do that to both sides. So I'm going to take 2.5 million divided by 4180, divided by 75, gives me a mass of 7.97. Probably call that 8.0 based on the sig figs we've been using. Now be a little careful here because we're done, but we're not done because it didn't ask us for the mass, it asked us for the volume. Well, fortunately, it's water that we're dealing with, and for water we can use a density of 1 kilogram per liter, and so the number doesn't actually change. It's 8.0 liters. How about one more? You can stop anytime if you feel like you got this. Let's go and find the, oh, you might want to stick around for this one. This one's going to look a little different. What would the final temperature of a 750 gram block of aluminum be if 2.5 megajoules of heat were added to it from a starting temperature of 20? So this one's similar to the last problem in that we're using the same amount of heat, but this time instead of water heating up, we're going to heat up an aluminum block. So write our formula out, Q equals mc delta T. And this time it's actually the change in temperature that we don't know. So I am going to go ahead and start replacing what I do know. 2,500,000 joules equals the mass, which is not 750, it's 0.75 because we have to convert that into kilograms. It is aluminum is the new substance, so we're going to look up the specific heat and find that it's 903. And then we got the TF minus TI. The reason I wrote TF is because that's actually what we're looking for. That is the variable that we're trying to find. So I'm going to leave that, and I'm going to subtract it from, subtract 20 from it. And since it's 20 that I used, remember that my answer is going to be in Celsius. I could have converted, I could have used 293 there, and then my answer would have been in Kelvin. So to solve this, we're just going to divide out the parts that aren't in the TF minus 20. Divide out the 0.75, divide out the 903, do that to both sides, and that's going to get us, oh, that's not my favorite calculator. 2.5 million, divide that by 0.75 and divide that by 903, and you get a ridiculously large number. We get 3,691. 3,691 equals TF minus 20. So TF minus 20, that's, we want to know what TF is, so we're going to add 20 to both sides to get rid of that term. So that gives us an answer of 3,711 as our final temperature in degrees Celsius. Now, that seems like a ridiculously large number. We can always go back and check the number if we want. We found that the so final temperature is 3711. We can subtract that from 20, or subtract 20 from that to get 3691. So that's our delta T. And then times 903 times 0.75. And yeah, it spits out the 2.5 million joules. So we did it all right. Why did we get such a ridiculously large number? Because keep in mind that we just used this heat to heat up water, and we found that it made a reasonable amount of water, 8 liters. It's kind of a lot of water, but it's not ridiculously a large amount of water. We made several gallons of water to its boiling point with the same amount of heat as something that got this aluminum to a ridiculously high heat. One thing I didn't say in the problem, but I should have, is assume that there's no change of state, because if this aluminum's melting, which it might at that temperature, I'd have to look it up, but I'm guessing it would have a good chance of melting at a temperature that high. The thermodynamics actually changes whenever you change state. That's kind of a different lesson. But why such a huge number? Well, two things. One, we used a lot. We put all this same amount of heat into a much smaller mass, not 8 kilograms, but less than 1 kilogram. And the second thing is that the aluminum has a much higher or lower C value. It has a value of 903 versus 4180 for water. So it kind of makes sense that putting that same amount of water heat that got all that water to its boiling point is going to do a ridiculous amount of temperature change to something like a small piece of aluminum.